In this 1992 ad, Chevy claimed to make the most reliable trucks in America using this graph. Not only does it show that 98% of all Chevy trucks sold in the last 10 years are still on the road, but it looks like they're twice as dependable as Toyota trucks. That is, until you take a closer look at the numbers on the left and see that the figure for Toyota is about 96.5%. The scale only goes between 95 and 100%. If it went from 0 to 100, it would look like this. This is one of the most common ways graphs misrepresent data, by distorting the scale. Zooming in on a small portion of the y-axis exaggerates a barely detectable difference between the things being compared. And it's especially misleading with bar graphs, since we assume the difference in the size of the bars is proportional to the values.
Graphs can be used to help us understand what is going on, or to support a point someone is trying to make. The problem arises when people present graphs that mislead the viewer. Let's take a look at this graph I found on an article about life expectancy. It looks pretty good, right? But a graph should also convey some information, so let's take it away for a second and see if you remember what the single largest cause of death was. And the answer, of course, is heart disease! Wait, not cancer? Why does 32% look so much smaller than 31%?
Well, in making the chart look three-dimensional, the farther away regions look smaller.
Another reason the cancer looks so much larger is that our eyes tend to add in the sides of the cylinder to the perceived size of that section. Usually, to better understand the information, a simple pie chart would give a more accurate view. Misleading as they are, three-dimensional graphs are often used in an honest attempt to make the graph look nicer. But the way they distort perception can also easily be exploited. If you were a scientist applying for funding to research cancer treatments, or a food company trying to downplay the significance of diabetes, which graph would you want to use? If you see a graph like this, you need to ask yourself, is there a reason the presenter would want to take advantage of this distortion? So, let's make a list of the deceptive graph techniques as we go through the various examples. First on the list is having the graph distorted by making the pieces look larger or smaller than they should be. Let's take a look at another graph. Continuing on the topic of health data, we have a picture graph comparing the average life expectancy among different countries. It's basically a bar graph with colorful pictures to replace the boring bars. But the pictures make it hard to see the height of the people. Look at the beret that the Frenchman's wearing. Where is the top of him supposed to be? So let's add a vertical axis and a bar graph to get a better sense of the scale. Okay, so some of the heights are a little bit off, but that isn't our biggest problem here. We learned from the previous example to be wary of distortions in graphs. Is any of that going on? Well, yeah. Notice how Japan has about twice the life expectancy of South Africa. But it looks like it should be way more than that. That's because the picture is scaled based on the height. But what we really are perceiving is the area. When you double both dimensions in the Japanese picture, you actually quadruple the area, hence the perceived size. This sort of picture graph exaggerates the perception of different values. It can be very useful for a company that wants to demonstrate a difference between them and their competitors, making a difference seem much more dramatic. So let's add picture graphs to our list of ways that can be used to distort the information by making the images look larger or smaller than they should.
So we have seen that three-dimensional graphs often distort the information, but you have to be wary of regular circle graphs also. In this graph about who's going to pay for the new stadium, it looks like the city's only paying half. But the slices on the right side, the $10, $85, and $50 million respectively, are all about the same size. That doesn't make sense. In fact, if I add up the numbers on the right side of the graph, it only adds up to $145 million. So by reorganizing this to scale, I realize the city is actually paying for 65% of the total cost. So in this graph, the scale is distorted since the sections in the circle graph are not proportional to the size of the wedges. A similar problem occurs when the percents do not add up to 100.